Let's look at refraction of light. Refraction of light. When light enters from, let's say, a rarer medium to a denser medium, we know that light bends towards the normal. This is the normal. Light bends towards the normal when it enters from rarer to denser medium. We also observe in such cases what there is some changes to the wavelength and velocity of the light. The light rather appears to slow down. Let's look at what happens there. And we also see that the light bends. Why does this happen? Let's try and discuss these two things. Now, when light enters from rarer medium to denser medium, what actually happens here is at the atomic particle level, let's say this denser medium has a lot of atomic particles, atoms spread out here. And remember, the light is also energy. So when light hits the atomic particles, what happens? The electrons in the atoms, the electrons that are there in the atoms, start vibrating at some frequency. Now, if that frequency, or rather, they absorb the energy from the energy from the light is absorbed by the electron, and because of that, electrons start vibrating in the atomic particles. If the frequency of the vibration of the electron matches with the natural frequency of the electron, then all the energy, most of the energy is absorbed, and then it heats up the material, it vibrates the material, and so on and so forth. Now, what is natural frequency? Let's say I have a string that is tied to two filaments and it has a mass m. Now, when I pluck at the string starts vibrating, right? Just I pluck it once and leave it. I do not force it to move in some particular frequency or anything. It has a certain mass and there is a certain tension there. Depending on the mass and tension, the vibration that happens here will be at a certain frequency. This is called the natural frequency of the particular material. Now, the electrons also have certain natural frequencies in each material. So, when the energy from light is absorbed by the electron, if it starts vibrating at the natural frequency, if it starts vibrating at natural f, the electron, then what happens is all the energy is absorbed in and is used in heating and vibrating the material. Now let's say the electron is not vibrating at the natural frequency. When light hits the subatomic particles and the energy is not absorbed by the is absorbed by the electron, but it does not vibrate in the natural frequency. Then what happens? When it's not vibrating in the natural frequency, it just absorbs the energy and then re-emits it. It absorbs the energy, re-emits it. Light continues to travel. It absorbs, re-emits, absorbs, re-emits. And because of this, light appears to slow down. In other words, if I have, let's say, these kind of these subatomic particles, electrons here, and when light comes here, it's traveling at the natural speed of light in vacuum. When it hits the electron, it's absorbed, not at natural frequency vibration, it's re-emitted. So light is at its natural speed here, natural speed, speed in vacuum here, speed in vacuum here, and speed in vacuum here, it matches. But because it's absorbed and re-emitted, absorbed and re-emitted here, absorbed and re-emitted here and here, there is a slowdown that happens. So light actually, the speed is not reduced in between the electrons in the vacuum. It is only due to the absorption and re-emission there is more time taken. So when light travels through the denser medium or any medium, there is this change in speed. And we know that the wave equation is c equals f lambda. Now we have seen that there is a change in speed, which is c, velocity. What happens to the frequency? The frequency is going to be the same. Assume that I have a rope and I keep oscillating the rope with my hand at the same rate. I keep moving it up, down, up, down, up, down, the same rate. I'm not going to change the frequency. So the same source from which this light is coming, the source is not changing. So the frequency remains same. So if the velocity goes down and frequency remains same, then naturally to compensate that, the wavelength will go down, right? So let's say 10 equals 2 times lambda, and then what will be lambda? It will be 5. Now 10 becomes, let's say, 12, and 2 is not going to change. Naturally, lambda has to become 6. So you see that the wavelength increases if the speed increases, the velocity increases. Now in this case, when it comes to denser medium, the velocity reduces. The velocity reduces, and hence the wavelength also reduces. So that's why wavelength reduces, frequency remains same, and velocity reduces when light enters from rarer medium to denser medium. But why does it bend in that case? So this is about the speed, but why does it bend? I've gone through various explanations and tried to logically, arrive at some explanation. But the best one that I've got is what I'm sharing here. When light is, of course, electromagnetic, so there is a electric field, and the direction of the electric field is perpendicular to the direction of travel of light. Suppose this is the direction which the light is moving, then the yellow vector or the arrow shown here is the direction of the electric field. So this is the electric field. Now we can always, since it's a vector, we can always split it into two components. One is horizontal to the surface which separates the two mediums, the rarer and the denser medium. This is a horizontal component, and there's a vertical component of the electric field. Now when it hits the surface between the rarer and denser medium, the horizontal component always is traveling along the surface, and when it enters the denser medium, again the electric field can be split into horizontal and vertical components. The horizontal travels along the surface at the point when it hits the surface. But what happens to the vertical component of the field? Because it's traveling in a denser medium with a different refractive index and so on, it becomes shorter here. The vertical component of the electric field becomes shorter as compared to the vertical component of the electric field in the rarer medium. When the vertical component becomes shorter, the resultant vector you see here, E, changes direction and becomes different. This is a different vector. This E is different from this E. Because this changes direction, this E changes direction, and perpendicular to that is the direction of travel of light. Light has to align itself perpendicular to the field, and hence it bends. So the explanation here is that, maybe you can comment if you think otherwise. The explanation here is that it's more about the field. The field is traveling towards the denser medium. When the field hits the denser medium, the vertical component becomes smaller, and hence the overall field changes direction, and hence being perpendicular to the field, the light also changes direction and bends. The reverse is what happens when it goes from denser to rarer, but this is the case of rarer to denser. Thank you.